Let's say we have a ramp and we have this box on the ramp that's 5 kilograms. And for the moment, let's assume that there's no friction. No friction at all. The object can just freely slide down the ramp. And we want to figure out what's going to happen to this object. So what would you expect to be going on here in terms of forces? What forces are acting on the object?
Gravity and normal force.
Yeah, and we could draw this as just, if we think of this as just this object as a single point. We draw the box as a single point, and we have force of gravity, which is pointing in which direction?
Just down.
Yeah, gravity would be pointing straight down. And how strong should we expect that force vector to be? What would be the magnitude of the force vector?
50 newtons.
Yeah, if we assume gravity is approximately 10 meters per second squared, really closer to 9.8, but we'll round it off for now. And the force of gravity is, at least the magnitude, is the mass of the object times the acceleration of gravity. So mass times acceleration of gravity, in this case, would be 50 newtons. So we've got an object that's experiencing 50 newtons of force straight down from gravity, but it's not falling because what else is affecting it?
The normal force.
And which direction
push from the surface? The normal would be perpendicular to the surface, so kind of at an angle.
Yeah, normal literally means perpendicular to some surface. So we're going to have a force that is in that perpendicular direction. The normal force, let's say F sub n. And do we know how strong that's going to be?
Probably not without calculating it.
Yeah, we're going to need some further calculations here. Sorry, what was that?
Oh, no, go ahead.
The thing is, it would be 50 newtons if the ground was level. If you just had flat level ground and the box here, in that case, you'd have gravity pulling down with a strength of 50 newtons. And in this case, which direction would the normal force be?
Up.
Yeah, it'd be straight up. And in this case, if the box is just resting flat on the ground, what should we expect those forces to add up to?
0.
Right. If there's no acceleration, acceleration is 0 if and only if. We often write if and only if as just IFF as an abbreviation. The acceleration equals 0 if and only if the sum of the forces acting on the object is 0. In this case, we know the box is not accelerating. It starts off at rest and continues to be at rest. It's not really important that it's at rest. What's important that is it's not changing its motion. So that means that the forces have to add up to 0. If we've got 50 newtons of force downwards, we've got to also have 50 newtons of force upwards, which can be provided by this normal vector because it is straight up.
So if the problem said that the box was moving at a constant velocity, like to the east, then we could still use this exact same setup because there's no acceleration.
Exactly. Force doesn't cause velocity, force causes acceleration. That is, the sum of the forces on the object equals mass times acceleration. If the velocity is constant, no matter which direction it's going, no matter how fast it's going, as long as it's moving at a constant speed in a straight line, the acceleration is 0. So that means the forces have to add up to 0. The only time you'd have a non-zero total force is if the acceleration is not 0. That is, if the velocity is changing. Maybe the object's getting faster, or maybe it's getting slower, or maybe it's moving in a curved path. Those all count as acceleration. Even if it's moving in a curved path at constant speed, the fact that it's changing its direction of travel, that counts as acceleration because velocity includes direction. But if it's not changing its velocity, if acceleration is 0, then you know the forces have to add up to 0. And that's true component by component. So you can say the y components add up to 0, and separately the x components also have to add up to 0. Forces can be treated one at a time like that. In this case, though, can these forces cancel out?
No.
No, there's no way they can add up to 0 because the normal force and the force of gravity are not in exact opposite directions. So that means that in this case, the forces will not add up to 0, so there will be acceleration. There's a net force, so that means there will be an acceleration. And to figure out which direction and how fast it's accelerating, first of all, as long as it stays on the ramp, what are the only directions it could possibly be accelerating?
Down, or like down the surface?
Yeah, downhill along the surface, or possibly uphill along the surface. Though in this case, that's probably not going to be what's happening. But we at least know the acceleration has to be parallel to the surface. It's not jumping off the surface. It's not crashing through the surface. Any acceleration has to be parallel to the surface. So in a case like that, if we know what dimension the acceleration is going to be on, at least in terms of an axis, in that case, it's generally a good idea to set up your coordinate system based on the direction you know acceleration is going to be. We can expect acceleration will be either straight diagonally uphill or straight diagonally downhill. So let's use that as an axis. We could call this the parallel axis, parallel to the surface. And this we could call the perpendicular axis, in the sense that it's perpendicular to the ramp. Would static friction force be present if the box is not moving? It could be. Static friction is the friction of an object that's not sliding on a surface. Like if you got an object on a surface and maybe something is pushing on it, but it's not actually moving, what's holding it back, what's preventing it from moving is called static friction, the friction of an object that's not actually moving yet. However, there doesn't have to be static friction. Like in this case, if nothing's pushing on the box, gravity's pulling it down, the normal force is enough to counteract that. So in this case, there would be no friction at all. However, if there was somebody pushing on the box, but not hard enough to actually move it, the person's exerting a force, let's say to the right. So we've got a force from the push, but the box isn't moving because there's exactly enough static friction to balance that out. Force of friction. And the force of static friction is somewhat flexible. Static friction is not a fixed amount. Static friction is going to push back with whatever force is needed to balance out the push forward, up to a certain point. There's a certain maximum amount of friction that static friction, a maximum amount of force that static friction can provide. If you push with more force than that, what's going to happen?
The box will move.
Yeah, the box is going to accelerate, start moving. And as soon as the box is in motion, as soon as it's sliding on the surface, then instead of static friction, you now have kinetic friction. Kinetic friction is different in a couple of ways. First of all, it's typically weaker than static friction, which is why it may take a lot of effort to get something moving, but once it's moving, it's much easier to keep moving. And also, kinetic friction applies a constant amount of force, whereas static friction can apply up to a certain amount of force, but generally just pushes with whatever force is necessary to counteract something else. So static friction is any amount up to a certain maximum while the object is not moving. Kinetic friction, while the object is sliding on a surface, is a fixed amount and is typically going to act in a direction against that slide. Any other questions on those forces so far? So let's go back to the example on the ramp. If there's no friction, just normal force and force of gravity, these will not add up to 0 because there's no way two vectors that aren't parallel can cancel each other out. So instead, there's going to be some component left over, some leftover sum of these. And that sum we know has to be in the direction parallel to the ramp, either diagonally uphill or diagonally downhill, presumably downhill. So what we would do here, instead of using the usual XY components, we would split these up into a parallel component and perpendicular component. Because that way we can figure out how much of it is in the direction along the ramp. That's what should be left over. And one advantage of this is that the normal force is already purely in the perpendicular direction. So we don't need to split that into components. We could certainly write it as, if we split it up into like parallel comma perpendicular, this has no component in the parallel direction. So its parallel component would be 0. Its perpendicular component is the whole thing. So just Fn. Whereas gravity, we want to split up into components. Gravity is going to have a parallel component and a perpendicular component. And those would form a right angle, of course. So we've got this right triangle. We know the hypotenuse is 50 newtons. We want to figure out how it splits up into the parallel side and the perpendicular side. So let's try writing that out, zooming in on that triangle. We could call these components the parallel component of gravity, let's say FG parallel, and the perpendicular component of gravity, FG perpendicular. Any thoughts on how we could figure out what those values are based on the 50 Newton hypotenuse we know? Or what other information would we need to figure out first before we can solve this triangle?
An angle somehow, maybe using the 20 degrees in the initial diagram.
Right, we're going to need some angle here in order to get the rest of the information about the triangle, so we can use trigonometric functions. And yeah, this 20-degree angle is a good starting point since that's the only angle we have. So if we know this angle is 20 degrees, but we want to find, going back to this triangle here, not that triangle, straight down, and this perpendicular. We want to find one of these angles. How could we figure out one of those angles using only the 20 degrees we already have?
Would it be like, since that one's 20, if you drew like a line straight down, the other one would have to be 90, and then that means that that other angle would have to be.
Mm-hmm. Yeah, that sounds like a good way to do it. Anytime you have, if you have some triangles, you at least know what the angles in the triangle have to add up to. If you don't have the triangles that link things together, it's often useful to try extending lines further until they do form a triangle. For instance, if we extend this horizontal further to directly under the block and extend this vertical, the direction of the force of gravity, the line of action as we usually call it, straight down further until it intersects, we now have a right angle. And now this triangle, that's a 20-degree angle, that's a 90-degree angle. What's left for this one?
180 minus 110.
Yeah. Or as a shortcut, if you're talking about a right triangle, you've already used up 90 degrees guaranteed. So what's left over for the other two angles?
90.
Right. So in any right triangle, the two acute angles have to add up to 90. We've already used up 20, so we've got 70 left for the other one. So this angle, the angle the force of gravity makes with the surface, is 70 degrees. Which also means, what's this smaller angle going to be?
20.
Right. That is, the angle that the force of gravity makes with the perpendicular side is going to be 20 degrees, which is the same as the angle of the ramp itself. That is, the angle that vertical makes with perpendicular is the same as the angle that horizontal makes with parallel. In fact, these end up being similar triangles. This triangle formed by the ramp, the horizontal, and the vertical is similar to the triangle of the force of gravity, its perpendicular component, and its parallel component. So there are a couple of ways we could go about this now that we know the angles. First of all, I would typically use the 20-degree angle simply because that's part of the given information already. It's usually a good idea to use the given information whenever possible, rather than extra numbers derived from the given information. Because if we had made a mistake finding the other number, then that mistake would carry forward if we used it in calculations. But if we use this 20, we know that's 20 degrees. So we can be much more confident in our results if we go back to getting information from the original given numbers as much as possible. And based on that 20 degrees, and we know this 50 Newton hypotenuse, how would we find, for instance, the perpendicular component of gravity?
50 cosine 20.
Yeah, because the
Negative.
perpendicular side is adjacent to that 20-degree angle. So cosine of 20 degrees would be adjacent over hypotenuse. That's the perpendicular side over 50 newtons. So FG perpendicular is 50 newtons times cosine of 20 degrees. And cosine of 20 degrees, you can look up on a trig table or type into a calculator. Make sure you're in degree mode. So 50 times cosine of 20 is about 47. So that means gravity is, it's 50 newtons straight down, but we could think of that as 47 newtons into the ramp direction, and also some amount in the along the ramp direction. And how would we figure out the parallel component? What would be the only difference we need to use?
Sine.
Yeah. Instead of having cosine being adjacent over hypotenuse, we could say sine of the angle is opposite over hypotenuse. So that'll be the parallel component over the hypotenuse. So the parallel component is 50 times sine of 20 degrees. Alternatively, you could also use cosine of 70 degrees. Cosine of one angle and sine of its complementary angle will always be the same. In other words, if two angles add up to 90, if they're complementary, then sine of one of them will be the same as cosine of the other. So 50 times sine of 20 will be about 17. And I'm rounding off a bit here, but this should be pretty close. So that will give us the parallel and perpendicular components of gravity. We can say that gravity, instead of saying gravity is 50 newtons straight down, we can write it in terms of its parallel and perpendicular components. Its parallel component is 17 newtons. And its perpendicular component is 47 newtons. But we probably want to call out of the surface positive. So let's call into the surface negative. So we'll call that negative 47 newtons. And that's just a matter of how we're defining our coordinate system. You could just as well call into the surface positive and out of the surface negative. I just think it might be easier to treat out of the surface as positive in terms of conceptually understanding what's going on here. So those would be the components of gravity. Even though it's straight down, we're not splitting it up into traditional X and Y components. We're splitting it into parallel and perpendicular components. Any questions on that so far? And by the way, even if we didn't have the angle, we could still figure out this information if we had some measurements about the ramp. Like if we knew, for instance, the length of this side and the length of this side, if we knew those distances, we could still figure out how this splits up. Because what do we know about these two triangles?
They're similar.
Right. The matching angles mean these are similar triangles, and that tells us the sides are proportional. So the ratio, for instance, of the hypotenuse to the long side of this triangle is the same as the ratio of hypotenuse to long side of this triangle. So you could set those ratios equal to each other and solve for the one unknown side, if you know all the sides of this triangle, or at least two of them, and then you can use the Pythagorean theorem to find the third. So you don't have to know the angles. You could figure it out from these sides if you know enough of the distances on this ramp. Any other questions on that so far? So let's put all these forces together then. Going back to Newton's laws, we know that the forces, normal force plus gravitational force as vectors, what should we expect all the forces on the object to add up to?
0.
0 if what? What has to be true in order for the
There's no external forces.
Well, not if there's no external forces.
If
there are external forces.
There's constant velocity or it's not moving.
Right. If there's no acceleration, then we know the sum of the forces must be 0. And it might be moving, it might not be moving, but the important thing is its velocity changing? If the velocity is changing, then there's acceleration. So the forces do not add up to 0. In this case, would you expect this to be constant velocity, or is it changing its velocity as time passes?
Changing.
Yeah. We know these forces don't add up to 0. There's no way two different directions can add up to 0 like that. They're not parallel. So that means this is going to be accelerating, but we can expect it's only going to be accelerating along what direction?
The parallel.
Yeah, it's only going to be accelerating along the parallel direction, which means it's very useful in cases like this to split up the equation into components. We can split this up into an equation with just the x components, or let's say just the parallel components. The parallel component of gravity plus the, or I started with normal force, parallel component of the normal force plus the parallel component of gravity equals mass times the parallel component of acceleration. And separately, the perpendicular component of the normal force plus the perpendicular component of gravity equals mass times the perpendicular component of acceleration. And of course, mass doesn't need a perpendicular or parallel subscript because mass is a scalar. It doesn't have components anyway. But we're splitting each of the vectors into its components and rewriting this equation, this vector equation, as two scalar equations because each vector has two components. And what do we know about these? For instance, normal force. What do we know about the parallel component?
It's 0.
Yeah, exactly. The normal force has 0 parallel component. It's purely in the perpendicular direction, so its parallel component would be 0. So normal force, the parallel component is 0, but the perpendicular component is the whole thing. So we could say the perpendicular component of the normal force is just the magnitude of the normal force, which we would sometimes write in absolute value bars or double absolute value bars. But typically, if you're using this vector sign, this little arrow to represent this quantity as a vector, writing that same variable without the vector sign traditionally means the magnitude of that vector. So magnitude of the normal force, which is the whole thing, which is the y component here, or sorry, the perpendicular component, plus, and then for gravity, we know the parallel component and perpendicular component as numbers. Gravity's parallel component is 17 newtons. Perpendicular component is -47 newtons. And then we also know the mass of the object, 5 kilograms. So we could fill in 5 kilograms. And what do we know about the acceleration in terms of parallel and perpendicular components?
There's only acceleration in the parallel.
Right, there is parallel acceleration. There's no perpendicular acceleration. So we can say the acceleration, presumably some downhill direction, is going to be 0 in the 0 in the parallel direction. And we were already calling the direction gravity is pulling positive, at least positive in the diagonally downhill direction. So we'll treat this direction as positive. And the whole thing is the parallel component. So we can just say A is the parallel component and 0 is the perpendicular component. So A parallel would just be A as the magnitude. And then A perpendicular would be 0. We now have two equations and also two unknowns. We don't know the acceleration and we don't know the normal force. But now that we've got two equations, we can solve for those two unknowns. In fact, in this case, this is separable. There's no interplay between A and Fn because this equation has only acceleration as the only unknown. This equation has normal force as the only unknown. So we can solve each of these separately. How would you isolate A, for instance?
Divide by 5.
Yeah, so 17 over 5. And newtons divided by kilograms as the units. 17 over 5 would be 3.4. And what happens when you divide newtons by kilograms? What does newtons actually mean?
Kilogram meters per second squared.
Yeah, newtons means kilograms times meters over second squared. We're dividing by kilograms, so that cancels out the kilograms. We're left with just meters per second squared. So we now know the acceleration. The object is going to accelerate in the down the slope direction, the diagonal downhill direction, at a rate of 3.4 meters per second squared. And at the same time, we can also solve this equation for normal force just by adding 47 newtons. We've got F normal plus -47 equals 0. Add 47, we get normal force is 47 newtons. So we now know the normal force. Nothing in the parallel direction, but exactly 47 newtons in the perpendicular direction. So the normal force is 47 newtons because it's got to counteract not all of gravity, but just the perpendicular component of gravity. And whatever is left, the parallel component of gravity, is the total force that provides the acceleration. So we now know how strong the object is pushed into the surface, 47 newtons worth of contact force. And also we know how fast it's going to be sliding downhill. This also means if you were to put a scale in between the ramp and the box, if you just have a scale for weighing things and put that in between the ramp and the box, assume everything's still frictionless, so the scale with the box on it is going to slide downhill. What measurement would show on the scale for the weight? What would the readout on the scale be?
Would it be 47?
Yeah, the scale is measuring the normal force, so the scale is going to display 47 newtons. We usually think of a scale as displaying weight, because that's what we usually use it for, but the scale actually displays the normal force. If the object is not accelerating, if you're just standing still on flat ground, then the normal force balances the weight because they've got to add up to zero anyway. But in this case, the normal force is not the opposite of the weight because it's on a slope and there's this acceleration going on. But in general, a scale will always display the normal force, or more specifically, the magnitude of the normal force. So that scale is going to say 47 newtons, which is not the actual weight of the box, but it's how strongly the box is pushing into the scale. Any other questions on that so far?
So if this problem was altered and there was gravity, or sorry, friction, we would have on the body diagram friction going in like the negative y direction, right?
Yeah, or in the opposite parallel direction.
Or sorry, yeah. And so if the box, like if it was enough static friction to where the box wasn't moving, then would we have a force from the surface? Like instead of having a normal force, well, like the normal force would still be perpendicular, but then with the surface, is that always in the opposite direction of gravity?
Well, let's try adding that in. Let's go ahead and assume there is friction. And let's assume that there's exactly enough friction such that this box is not sliding. So let's say there is friction and it prevents the box from accelerating. Or let's say it prevents it from moving entirely. The box is just staying still. So if the box is just staying still, then what do we know about the acceleration?
There's none.
And therefore the total force?
0.
Yeah, total force would have to be 0 because there's no acceleration. In that case, there has to be some other force because we know that gravity and normal force together create a down the slope force in total. There's got to be a pushing back up the slope force, and that presumably is the force of friction. So friction is going to be diagonally uphill because friction has to be parallel to the surface, and it's going to be parallel to the surface in a way that counteracts whatever other force it's balancing. So here's the force of friction. And without even doing any more calculations, just based on the calculations we've already got, how strong would that force of friction have to be to balance everything out?
3 newtons.
3 newtons? Because?
I don't know. I thought it was because gravity was 50, the normal force was 47. And so then.
Well, we're not adding a scalar stuff. We're not adding.
Wouldn't it just be the opposite of the parallel component that we already found?
Because if you look at this in terms of the components, friction has a parallel component, but no perpendicular component. So in terms of components, it's going to be backwards. So we'll call that negative some force, and it has no perpendicular component. So the components of the force of friction would be negative force of friction, comma, 0. If we include that in our equations here, it has no perpendicular component, so it does not influence the perpendicular equation at all. But it does have a parallel component, so we'd include negative force of friction here. Also, we'd be assuming that the acceleration in the parallel direction is what? Yeah,
0.
0. So now instead of having normal parallel plus gravity parallel equals mass times acceleration, we instead have all three of these add up to 0. However, the parallel component of the normal force is still 0 because the normal force has no parallel component. So instead we just have negative force of friction plus 0 plus 17 newtons equals 0. So now what does the force of friction have to be?
17.
Right, that's got to be 17 newtons because it is specifically balancing out the parallel component of gravity. So this tells us the force of friction. Force of friction has to be 17 newtons.
Can you explain one more time why it doesn't add up to 0?
They do add up to 0. Specifically, the vectors add up to 0. Remember, forces are not scalars. So if you wanted to visualize the sum of these forces, let's say we have this XY coordinate plane. If we add these up as vectors, we've got force of gravity straight down 50 newtons, plus the normal force this way 47 newtons. And then from that as our new starting point, we add force of friction, 17 newtons. That gets us back to the starting point. If these vectors added together head to tail geometrically return back to the starting point, that means they've canceled each other out. No two of them individually cancel out, but all three of them together add up to 0. And since this happens to be a right triangle, friction and normal force are perpendicular. You could even check this with the Pythagorean theorem. You've got 50 here, and this was 47 and 17 approximately. So 17 squared plus 47 squared, take the square root of that, you should get pretty close to 50. It'll be a little off because we were rounding these values, but should be pretty close. So the numbers don't add up to 0 unless you split it into components, but the vectors add up to 0, and that's what's important, since direction actually matters here. Any other questions on that so far? And since we know the friction force and the normal force, that also gives us one more piece of information. Have you seen the idea of coefficient of friction yet? Does that sound at all familiar?
I don't think so.
The idea is if you've got an object on a surface and let's say you're trying to slide it, the amount of friction is going to depend on partly the materials they're made of, but also how hard it's smashed into the surface. Like if it's just resting really lightly on the surface, friction is very easy. If you smashed into the surface really hard, there's much more friction, there's much more interaction. So it turns out that friction, if you look at this in terms of magnitude, ignoring direction for the moment, the amount of friction is proportional to the amount of normal force, which means that one of them equals a constant times the other. Specifically, we usually write this as force of friction as the magnitude equals a number called the coefficient of friction, the Greek letter mu, times the normal force. And the coefficient of friction is just some number between 0 and 1, depending on the material the objects are made of. And I usually think of that as representing what percentage of the normal force also acts as a friction force. It's just the ratio of those two. And typically, if you knew the material, you could just look up the coefficient of friction on a data table. But we can actually solve for that now because we have both of these values. Force of friction over the normal force as magnitudes. We know the force of friction in this case is 17 newtons. We know the normal force was 47 newtons. So if we divide those, that'll tell us the coefficient of friction. So about 0.36. And note that the newtons cancel out. So coefficient of friction is a unitless quantity. This is essentially saying whatever the normal force is, the friction force will be 36% of that. So this will work. This object will be able to stay still on this slope if the coefficient of friction is 0.36 or greater. Anything more than that will still have enough friction to hold it still. So as long as the coefficient of friction of these materials is at least 0.36, then this will work. This object will stay still on the slope. Any other questions on those forces? And let's take a quick look at momentum as well, because that's going to be another important topic here. If you're dealing with an object, or let's say two objects, let's say you've just got a couple of rocks floating in space, so you don't have to worry about any other forces. Let's say you've got a 20 kilogram rock. Let's call that object A, and a 5 kilogram rock, object B. And let's say object A is moving to the east at 6 meters per second. And object B is moving to the north at 5 meters per second. And let's say they collide and stick together. So we now have object AB, a 25 kilogram rock. And approximately which direction would you expect that to be traveling?
I have a quick question.
Mm-hmm.
Our professor said for our quiz, we're only doing 1D momentum problems. So this isn't something, like we don't have to know this one. This is 2D, right? Is my question?
Yeah.
Because there's multiple components.
Yeah.
Okay, so 1D just means it either only has X or only has Y components?
Yeah, and of course it doesn't have to be horizontal or vertical. If everything's moving along some single straight line, that counts as one-dimensional. And you can essentially just treat the X-axis.
Okay, I was just kind of confused by when we're talking about 2D versus 1D collisions.
Yeah, as long as everything's moving along a single straight line, no matter which direction that single straight line is, that counts as one-dimensional.
Okay.
And in a one-dimensional case, you can kind of treat the vectors as scalars and use positive or negative to keep track of direction. But in this case, if we've got a rock moving to the east and a rock moving to the north, and let's say they collide and stick together, yeah, presumably the result will drift off, not exactly to the northeast, but somewhere northeast-ish. So we don't know exactly which direction, and we don't know how fast either. But we can use the idea of conservation of momentum to figure that out. And typically what we do here is we set up this idea of a momentum chart using the initial momentum, change in momentum, and final momentum as columns. And then set up a row for each object and also a row for total. Ultimately, the whole point of this is just organizing information in the idea of conservation of momentum. The idea is that the initial total momentum should equal the final total momentum under what circumstances? What has to be true for the momentum to not change overall?
No external forces?
Right, if there's no external forces, which is the case here. The objects are applying forces to each other during the collision, but those are internal forces. A applies a force on B, B applies a force on A. Those are all part of the system. There's no other forces from outside, like there's no gravity, no wind, no air resistance, nobody sneaking up and hitting it with a baseball bat when you're not looking. So this is a closed system. If it was an open system, we'd say the total initial momentum plus any impulses, usually written as J, equals the total final momentum, where impulse is force times time. And the reason that works is if you write out force as mass times acceleration times time, what do you get if you multiply acceleration times time?
Meters?
Not quite, because how do we define acceleration? What does acceleration mean?
Meters per second squared.
In terms of units, yeah. So that would be, as a definition, acceleration is change in velocity over change in time. So if we multiply mass times acceleration times change in time, the delta t's cancel out and we're left with mass times delta v. In other words, change in momentum. So an impulse, that is a force applied for some amount of time, creates a change in momentum. But if there's no external impulses, or maybe there are some external impulses, some external forces applied for some amount of time, but they add up to zero, then we can assume that the total momentum doesn't change. Which means we can fill in a zero in the change in total momentum spot right away. There's no change to the total momentum. And I would write that as a zero vector because it's not just the number zero, it's a vector whose components are all zero. We can also fill in the initial values. How would we find the momentum of rock A?
20 times 6.
Yeah, 20 times 6, so 120. And momentum has direction, so that'll be 120 to the east. Probably draw that a little bigger. And we can also write that as components. That's 120 to the east and nothing to the north or south. So we'll write that as 120, 0. And likewise, rock B is going to be what?
25.
Yeah, 25. And in terms of direction, that'll be 25 to the north. So we can write that as components also. 0, 25. Because it has no east or west component at all, it's purely to the north. And then for total, how would we add these together?
Would it be 120, 25?
Yeah, we can add the components individually. 120 plus 0 is the new x component. 0 plus 25 is the new y component. So that'll be 120 to the right or to the east and 25 to the north. So it'll be along this diagonal. And if we need to, we could also find the magnitude and direction. But in general, if you're going to be doing any further calculations, it's a good idea to leave everything as XY components because that makes the calculations much easier. At the very end, it's often a good idea to go back and convert any XY components to magnitude and direction if they're values you care about. But I would just leave it as XY components for now. Because now what do we also know about the total final momentum?
It should be 120 or yeah, 120, 25.
Yes. There's no change, so we should expect final to be the same as initial. Or more generally, you can add initial plus change to get final. 120 plus 0 is 120, 25 plus 0 is 25. But in general, for any closed system, if there's no external impulses, or if the external impulses add up to 0, final total is the same as initial total. But the individual values can change, they just need to add up to the same final total. And if we know these rocks stick together, they're combining into one object, but as far as the chart is concerned, we're still considering them as separate objects. So instead of thinking of it as one 25 kilogram object, we could think of it as a 20 kilogram object A and a 5 kilogram object B that happen to be traveling together. If they're traveling together, what has to be the same? Right, they've got to have the same final velocity. Note that their final momentums are different, but they have the same final velocity. So V final A equals V final B. If we write each of these as mass times velocity, so 20 kilograms times V final, and 5 kilograms times V final, we don't know what V final is, but we know it's the same V final. So if we add those up, since it's the same V final in both, what can we do with that?
Factor it out.
We can factor out V final and get 20 kilograms plus 5 kilograms times V final. In other words, 25 times V final. In other words, the total mass times that final velocity, which we can only do because it is stuck together. And then that has to equal the total momentum that we know it equals, 120, 25. And I've been leaving out the units, but this should all be kilogram meters per second. Then how do we solve for V final?
Divide by 25.
Divide both sides by 25. And since this is in terms of components, we would just divide each component by 25. So 120 divided by 25 would be 4 4/5, so 4.8. And then 25 divided by 25 would be 1. Kilograms cancel out, so we're left with meters per second. So we now know, even though we don't know we haven't figured out the momenta yet, we can say that the final velocity has components that we now know. 4.8 to the east and 1 meter per second to the north. If we wanted, we could then fill in the rest of the chart by multiplying 20 kilograms times both of these to get the momentum components for A, and 5 kilograms times both of these to get the momentum components for B. And those will end up being a medium-sized vector in this direction and a short vector in this direction, but they add up to this same total. You could then also subtract component by component to get the changes, which would tell you how much impulse each one's experiencing. But if we just want to know how fast it's going, how do we figure out the speed here?
Pythagorean theorem.
Yeah, since we know two of the sides, we can use the Pythagorean theorem to find the missing hypotenuse. That'll tell you the speed, that is the magnitude of velocity. That's how fast it's actually going. And also as for direction, how would you find this missing angle?
Inverse tangent of 1 over 4.8.
Exactly, because whatever this angle is, its tangent has to be opposite over adjacent. That's 1 over 4.8. So take the inverse tangent of 1 over 4.8, and that'll tell you the angle it makes. So you describe it as that many degrees north of east. Any other questions on that?
Really quick, for the math you did on the right-hand side, why could we just divide 25 by the components?
Well, we're dividing the vector by 25. In general, if you divide a vector by some scalar, like let's say you've got a vector that's got some x component and some y component. Let's say this is vector u, and we've got ux and uy. If you're dividing this vector, let's say by 5, dividing it by 5 means you're getting a new vector that's 1/5 the size. It will also have 1/5 of the x component and 1/5 of the original y component. So if you're dividing a vector by some value, you can divide its components by that value individually. And same thing with multiplication. If you're multiplying a vector by a scalar, you can just multiply each component by that scalar.
Okay, that makes sense. Okay. So the units don't really matter just because we're in component form. So the 120 and 25, we're just looking at it as.
I would say the units do matter, but you can treat the units as being a multiplier outside the vector. So it's 120 kilogram meters per second, comma 25 kilogram meters per second. But since units are effectively a multiplier, you can pull the multiplier out of the vector and just say it's 120 comma 25 kilogram meters per second. Then when you divide by 25 kilograms, the kilograms cancel out, but each one of these is still being divided by 25.
Okay, that makes sense. Thank you.
You're welcome. All right, I've got to get ready for my next workshop, but I will see you next time.